Hello, math fans. Dr. Andy Levis going to talk about partial derivatives and how we study surfaces. Already in a previous video talked about contour maps and how we use those to try to visualize the surface if we can, such as the one you see here. But today we're going to talk about what if we walk along the surface. And I have a point sitting on there. You can see it. This particular surface is a paraboloid. It has the equation 9 minus x squared minus y squared. But I'd like to talk about the concept of what we mean by partial derivative and then give the definition and do a little bit of theory at the end to see how it matches up with Calculus 1. But it really just means slope. Now the problem is if you start walking around this thing, there's a lot of places you can stand and there's a lot of different slopes. So how do we make sense of this? So in our course, we're not going to study all the different directions you can look. We're only going to look at these two directions. So looking down at the contour map from above, we're only going to look those two ways. Either we're going to walk straight north or east. If, let's say the positive y-axis is north and the positive x-axis is east, and we're going to consider the slopes in those two directions. Now, those can be really different. In fact, the point I'm at right now, it's uphill if I go in the x direction and downhill if I go in the y direction. So let's pop this back out and actually look at that point and go to the surface. So how do I actually do that? What I do is I fix a variable. So what I mean by that is I'm going to replace one of these with a constant. So I'm going to fix, let's say I do f, and I pick a number. Like here, the point I'm at is about x equals -1. So we're going to do -1, y. The moment you do that, it becomes a one variable problem. It's -1 squared minus y squared. And so it's 8 minus y squared. And then what you've really done is you've found the intersection of the original surface with the surface x equals -1, which is actually a plane. I'm going to show that plane to you now. So here we're going to fix x equals -1. I'll do it in steps here. There it is. It's actually -1 point, I don't want to lie to you, -1.3. So let me make it exactly -1. So there it is, -1. We're standing at a point where the x coordinate is -1, and we're just going to study that 2D curve right there. So here's the actual curve. That's not the curve, this is the curve right there. We're going to ask ourselves what the slope is. Now the moment you do that, it just becomes a 2D problem, a 2D slope problem. And we can find the slope of a 2D thing by just taking the regular old derivative. Now at this point we could use a prime, but eventually we'll start using a little subscript because we don't want confusion about which variable we're working with. So we'll use this, or we'll say the partial of z with respect to y. So those are the things we're going to be computing. Okay, then you have a formula. In fact, if I plug into that formula, like y equals 1, here's what I get. The slope of that line is -2. So if y equals 1, then we can conclude the slope in the y direction at when x is -1, now that was already fixed, and y is 1 is -2. Getting that from here. Now I'm going to show you that line. It's right here. That slope has -2. Now as I look at it, it looks like it has a positive slope. So we have to agree on what we mean. We actually should be looking at it from this side. The slope of -2. So how do we know for sure? And that's what I was talking about, is we're only going to walk in the positive x direction or positive y direction. What we mean is if you take a slight step in the y direction, if you go 1 foot in the y direction, how far down are you going to go? That's all we're asking. So if you increase y by a little bit, then this is telling you the z is going to go down by 2. That's how we think about it. And that's kind of where this notation makes sense. It's the change in z over the change in y and not changing x at all. In fact, you could even add the change in x is 0. Okay, so that's one perspective. There's no reason we can't do the other perspective. So the other perspective is, what if we do the change in z with respect to x? You don't actually have to put a particular number in. You can just think about it as fixed. So if we think of y as fixed, and this is the only variable, with respect to x, then this is going to be negative 2x. And the partial, and with respect to x, at negative 1, 1, just to pick the same point, is actually going to be positive 2. And that says if the change in x is 1, then the change in z will be 2. And we're talking about when the change in y is 0. So it actually can be positive. It says it's uphill. Let's see if it's uphill the other way. So how do we do that? We fix the other variable. We're now looking at those cross sections, and we're finding those slopes. It's positive because if you walk in the positive x direction, you're going uphill. And those are those two slopes. So getting rid of everything else, let's get rid of the curve and the plane. The curve. And let's put the surface back up there. This is what we're doing. We're finding those two slopes. The slope in the positive x direction and the slope in the positive y direction. Positive x direction means to the right, viewed from above, parallel to that axis. You can see that's uphill. So if I walk to the right, it's uphill. Or towards us, it's uphill if I turn it like this. If you walk in the y direction, it's downhill. What's valuable is that we can compute those and actually find formulas for them anywhere. And in particular, when you're at the peak, the slope is 0 in both directions. It's possible to have the slope 0 in one direction and not the other. For example, here. It's like the bridge of my nose, I sometimes say. That's a place where the slope is 0 in one direction. We actually are going to eventually want to have the slope 0 in both directions in order to be at a high point. Okay, so there's a little taste of what the partial derivative concept is. It's only looking at these two slopes. Now, one natural question is, why can we just do the one variable derivative to compute this? Is that the same as the definition? So a little bit of theory to end this. I'll get rid of this. So you should remember that if I give you a one variable function and I say, what's the derivative? And you never knew what it was, it comes from doing the slope this way. It comes from simplifying this and then figuring out what happens when h goes to 0. Now, if that's too much there, that's just the rise over the run. That's y2 minus y1 over x2 minus x1. But you're going from x to x plus h, so that's why the bottom is just h, and you're plugging into the function to get the corresponding y's. But back in Calculus 1, we have students actually go through and do this, meaning they plug into the function and simplify and find the pattern. And if you find and expand, it's not very long, so maybe I'll just go a step further, make sure I stay on the page. You get x squared plus 2xh plus h squared minus x squared over h. And these cancel, and one of the h's cancel, and then you let h go to 0 and you get 2x, and that's where that came from. And that was just one of many examples, and then we built a collection of rules. Okay, so just for comparison, the definition, I'm going to grab it here, I've written it out, going back to our original function. The definition for a multivariable partial derivative is the same definition. So if you ever see this definition written out, it is no different. So when I say I want the partial with respect to x, what we mean by that, move this over a little bit so we can see it better. What we mean by that is we're actually fixing this variable. It's a constant. And the only variable we're considering is x. And it's actually the exact same definition. And what we mean by that is you plug into your function. You can see the x plus h there. You see we've kept the y the same. And when you simplify this is a fairly straightforward example, but a whole bunch of stuff cancels. This cancels, this cancels. And you end up getting negative x plus h squared minus x squared. And then you can do all the same stuff you normally do with one variable function. You get the same derivative rules. So that's the concept. It's actually the same definition. You just say, which variable do I want? You can think of it as you're going to take a slight step in the x direction. What's the slope? And then you're going to take a slight step in the y direction. And what we mean by that is in the positive x direction or positive y direction. And we're going to figure out what the slope is. And those can be very different. But the good news is we already have a tool to find them, a pattern for them, and we can just use the one variable derivative. All right, hope that gives you a starting place.